All right, good morning. We are going to finish our polar for 2020, and we're going to look at polar area today. So I've learned from some good feedback not to turn my iPad sideways, that it makes your screen go sideways, so I'll try to not do that anymore. Thank you for the person who pointed that out. All right, so we're looking at polar area. Now it's very similar to in the fall when we did area under a curve. So we were working in a rectangular system in the fall. So we had f of x, and we wanted to find the area under this curve. So what we were doing essentially was we were doing teeny tiny little rectangles. And we started with one huge rectangle, and we made smaller and smaller rectangles, and we started adding them up. And eventually we got to the place where we had the sum of the heights, and so f of x modeled the height of one of these rectangles. And then the width of each rectangle was infinitesimally small, we called it dx. And you did it from A to B, so the x coordinate where these heights started, all the way to the y coordinate, the second x coordinate where these heights ended. And that's how we find the area under a curve. Now we're going to look today at polar area, and it's a very, very similar concept overall. So we start with a nice circle. So the most basic polar curve is a nice full circle. So what we're looking at is finding a sector area. So you learned way back in geometry how to find the area of a sector. So a sector is like your slice of pie. So the way you did it in Geo was you did degree over 360 times the area of a full circle, because this represented a portion, a pi, a portion of the circle. So say this was 60 degrees for theta, well that was 1/6 of the circle. So when you put 60 degrees in for degrees, you got 1/6 of the full circle. So that's kind of how you went about it. Now, we're going to work in radians, of course. So instead of degree over 360, what we have is theta over 2 pi. So it's what portion of the entire circle, which would be 2 pi, am I working with when I'm finding the area of this sector. Okay, so the area of a sector is this formula. Not degree. Sector area. All right, now simplifying that, the pi's cross each other out. So what you get is r squared over 2 times theta. Now, that works great when you have a uniform radius. So it's a circle, so your radius is the distance from the center all the way around. Now, what's different about polar area is my distance from the center isn't going to necessarily be consistent. The distance from the center is changing at all times. So I need to allow for it to change. So what we're essentially doing is you're taking these sector areas, but you're finding tiny, tiny, tiny little sectors. Okay, and so what I'm doing is I'm calculating all these teeny, tiny little sectors from the origin out to these curves. And the smaller those sectors are, the more accurate they're going to be. So my formula comes from here. So the 1/2 just goes out front because it's just a coefficient. Integral, so it's the angle alpha where this sector, if you will, starts, all the way to the angle beta, which is where the sector ends. So instead of A and B in my rectangular system, we're working with alpha and beta, and because they're angles, just like theta. And then it's r squared. So the radius is just r. Now that's going to be an expression for us because my radius is fluid, it's changing. And then my width, if you will, of the sector is infinitesimally small when I become perfect, so it's d theta. So that's where this formula comes from. So that's the area of a sector, 1/2 the integral from alpha to beta of r squared d theta. All right, so doing some of these, the key is the decisions you have to make, really, are what are alpha and beta. So where does my area that I'm talking about really begin? What thetas control that? And if you really understood how we graphed polar curves, this isn't that difficult. But if you kind of struggle with graphing polar curves, that this can be harder. So that's one reason that I like to go through the graphing of them, and one reason it will really help you to be able to graph them in your calculator and check. So this is the most common question. It says find the area of one petal of the rose curve given by r equals 3 cosine 3 theta. So you should have went through rose curves way back in geometry. So there are different properties of these polar curves that you can learn from. So if I have cosine, and we would spend a day going through them, but we're not going to now. Thanks, Corona. But the coefficient, what you see is the coefficient is what's controlling how far your maximum petal length is. So if the coefficient is 1, then your maximum length from the origin is 1. If it's 2, then that length of that petal is 2. At 3, it's 3. All right. Now the next thing you'll see is the coefficient of theta is affecting how many petals you have. So if it was an odd number, so if it was 1, you got 1 circle. If it was 3, you got 3 petals. 5, you got 5 petals. 7, you got 7 petals. If it's an even number, it's a little more complicated. So even was double. And it has to do with the symmetry. And as you go around theta, what's going on in the odd is that you're overlapping yourselves. But in 4, you have 8 petals, etc., etc., etc. So that's what those numbers are. They're not just random things. So if I know all that, I can understand a little more. I can understand that 3 cosine 3 theta, the 3 out front, in the very front of cosine, is the length of the longest petal, and the 3 theta is what's controlling how many petals you have. All right, but I'm trying to figure out what's the area of one of them. The key is 1. There are lots of ways to do these. The only decision I got to make, so its area is 1/2 the integral from alpha to beta. So r here is 3 cosine 3 theta squared d theta. All right, so the only decision I have to make here is my alpha and beta. Everything else is already finished. So the question becomes, well, what angles control one of these petals? All right, other than just guessing and checking, the most important thing is the petal starts at the origin. And if you're on the origin, your radius is 0. So 0 equals 3 cosine 3 theta. So what this equation is going to give me is all the different theta values where my curve is going through the pole, or the origin, if you will. So I can solve this. So 0 equals cosine 3 theta. All right, so 3 theta. So the places where cosine equals 0. So cosine, remember, is your x-coordinate. So pi over 2. And then again at 3 pi over 2. And then again at 5 pi over 2. 7 pi over 2. And you go round and round and round. 9 pi over 2, etc. So theta is pi over 6. And then 3 pi over 6, which is pi over 2, 5 pi over 6, 7 pi over 6, 9 pi over 6, which is 3 pi over 2. So that's enough. Alright, so what I have here, these are the places where this thing starts. So if I were to go label my curve, when theta equals 0, I'm sitting here. So what it's saying is my curve is going this way, and then it's hitting the origin at theta equals pi over 6, and then it's passing on through. And then I'm hitting the origin again at theta equals pi over 2. To understand this, you really need to go in your TI-84 and put in your graph it. Okay, so go to polar setting and work and look at the different settings. Watch the little particle go around. So then it comes out this way and swoops around, and it's going to hit the origin again at theta equals 5 pi over 6. And then you go out again, and then it's back to where I started at theta equals pi. Okay, so if I wanted the whole rows, so if I wanted to find the entire rows, I would do 1/2 0 to pi of 3 cosine 3 theta quantity squared d theta. That's the entire rows. But my question is just one petal. So you got a lot of options. So option 1 is to find the whole rows and then divide it by 3. Okay. Option 2 is to isolate just one petal. So you could do the integral, so 1/2 out front. That's the thing everybody forgets, the 1/2. From 0 to pi over 6. And then you got r squared d theta. Now what that's going to give you, so if you think about it sweeping this way, you're starting at 0, you're pulling this area. 0 to pi over 6 gave you that. Now that's only half the petal. So what you got to do to this is you got to multiply it by 2. Okay, or your next option, if you didn't want to double half of a petal, you could do 1/2 negative pi over 6 to pi over 6 r squared d theta. That would give you the whole petal. And there's actually infinitely number of options here. Or you could do 5 pi over 6 around to pi over 2. Now that one is going to give you this petal, but they're all the same, of r squared d theta. And then to get your answers, you can just plug them in the calculator. Alright, so that's how the rows curve is. So I want you to stop the video now, or it's going to end, and I want you to actually plug each of these different intervals in your windows and see that they're all equal and they're all